EMC or electromotive compatibility is the ability of electrical equipment and systems to function acceptably in their electromagnetic environment without interfering by other devices. What is the goal of EMC and how? It is to build the correct operation of different equipment in a common electromagnetic environment by limiting the unintentional generation, propagation, and reception of electromagnetic energy, which may cause unwanted effects such as EMI or electromagnetic interference or even physical damage in operational equipment. What are characteristics of an electromotive compatible system? It does not cause interference with other systems, it is not susceptible to emissions from other systems, and it does not cause interference with itself. Why is EMC relevant to electricity and magnetism? Circuits and components generate magnetic fields when current flows through them. So EMC focuses on minimizing electromagnetic interference caused by these fields so electronics don't disrupt nearby devices. Electrostatic can discharge into sensitive circuits, causing malfunction or damage. So EMC designs circuits that can absorb or redirect the discharge safely by using electrostatic discharge diodes. Next, voltage change in a circuit can cause unwanted signals for nearby electronics via magnetic fields. So EMC reduces this by proper circuit layout, shielding, and grounding. Shielding is using conductive materials to block electromagnetic fields, while grounding is controlling unwanted signals.
Hi, I am Farah Atika and I'm going to explain about detail of exploration in EMC. In EMC studies, there are four basic coupling mechanisms, which is conductive, capacitive, inductive, and radiative. A coupling path can be based on one or more of these coupling mechanisms. Quite often, coupling paths are a complex combination of these basic mechanisms, making the path difficult to identify, even when the source and receptor are known. Currently, EMC is an integral part of electrical and electronic design. There are mainly three ways to prevent EMI, which is the first one is mitigate the radiated and conducted emission of the source. The second one is make the coupling path inefficient by electromagnetically separating the emitter and receptor as much as possible. And lastly, make the receptor less susceptible and radiated and conducted emission. Next, I am going to explain about real-world EMC implementation. First world implementation of EMC is automotive electronics. In the automotive industry, EMC is paramount due to high susceptibility of onboard electronics to electromagnetic interference from the vehicle electrical and mechanical system. One case study involved a manufacturer of electric vehicles, EVs, facing EMI challenges in their onboard charger. They implemented advanced filtering techniques, shielding, and proper grounding to contain EMI, ensuring that the charger wouldn't interfere with other vehicle electronics. As a result, their EVs not only pass regulatory EMC tests but also demonstrate improved overall performance, including faster charging times and increasing energy efficiency. The second one is smart home appliance and EMC.
EMC indicates whether a device can exist harmoniously within its expected operating environment. Benefits of EMC: boost reliability, shows that a product is compliant with established requirements and regulations. Next, it improves safety, prevents safety risk, product failure, data loss, and other adverse events. It reduces warranty issues where products cannot be recognized or taken to market unless all EMC testing requirements are met. Next, highlights potential issues, provides early detection of any possible interaction between electronic device and electrical system. And lastly, it reduces service costs, provide long-term service and manufacturing benefits for the product. Next is the challenges of EMC. It has stricter standards as new technologies such as 5G introduce new interference necessitating ongoing updates to EMC strategies. Next is high development costs and time frames. It insulating and shielding devices to prevent interference at financial constraints. Next and lastly, miniaturization challenges. As devices become smaller and more complex, maintaining EMC becomes more difficult due to limited space for shielding and grounding. Future developments and innovations. Integration of 5G technology, vehicles are becoming more connected than ever, which increase the substantial in electromagnetic interference, or EMI, like wireless communication signals. Testing for autonomous vehicles has introduced a new dimension of complexity, which includes self-driving cars, like Tesla. Next, environmental impact considerations. Automakers are looking for sustainable solutions to minimize ecological footprint of testing processes. And lastly, wireless power transfer. Ensure safety and reliability of wireless charging systems with a focus on preventing EMI that may affect other vehicle systems.